All right, so a couple things. These tree definition quizzes and tree operation quizzes, they are basically, if they're not the same questions that are on the beginning of my of exam two, they are very close analogs with just simply the tree operation quizzes has here, what's the tree after you do these things, or removing these trees would be various things. One thing that a lot of students have some trouble with is the difference for some of our tree definitions. So specifically, we've got three kind of definitions. We've got three types of trees and then one category that I kind of did not define. The first is so we've got our full, we've got our complete, and we've got perfect. I'll do the perfect second. Full is fairly straightforward. You've got a tree and every node has zero. It's a binary tree and every node has either 0 or 2 children. This is a full tree because everything has 2 or 0 children. The minute I add another node, it's not going to be full. A perfect tree is what you'd expect to see if I actually drew a tree in a textbook, which is that it would have basically all possible positions filled at a certain height, right? So H3 has 7, height of 3 has 7, height of 4 would have 15. Specifically, the way I define it is it would have 2 to the, that a perfect tree of height H, perfect binary tree of height H has 2 to the H minus 1 nodes, where H is the height of the nodes. Okay, so a brief aside, various textbooks do have different definitions of what height this tree would be. The definition I use is that this tree has a height of 4. 1, 2, 3, 4. But some textbooks use this definition, 1, 2, 3, for the number of layers of edges, which is correct. Honestly, I think the right one is, but people can make arguments on the left and declare it as height 0 because, hey, this would start at 0. Honestly, it doesn't matter so long as you're consistent in your definitions. But I've seen textbooks do it in separate ways. I don't know why, but that's honestly, it's not a big deal. The point being, though, is that if we use our definition for nodes, this has only one way of being. This only has one way that tree can look for a certain height. Okay, so basically, it's your drawing of a tree. This is your perfect tree. Next, we have our complete tree, and that's probably our trickiest one. A complete tree, okay, is very interesting. It is a perfect tree up to height H minus 1. So here, we're going to draw a tree of height 4, H equals 4. But our perfect tree here, okay, so we have a perfect tree of height 3, and then below that, we have all the nodes filled from the left to the right. Make sense? On the bottom. So this is a complete tree. So easier to show by example. This is a complete tree. This is not a complete tree because we have a gap here. Okay? So it's filled so that it's perfect on top, and then we have everything filled in left to right. The point of a complete tree is that it's embeddable into an array. Or embeddable into an array in a very easy way. So 1, 2, 3, 4, 5, 6, 7. So yeah, we have 7 nodes here on top. And then this node, right, it goes left to right this way. So if we delete this one, this is no longer complete. Right, it has a gap. You're not looking for any gaps. Being a complete tree, checking if something is full is actually pretty easy to do with recursion. Checking if it's perfect, pretty easy to do with recursion. I honestly struggle to think of a way to easily do that with complete trees. I will go back to complete trees in a second because I will briefly talk about heaps, but first I need to talk about one other thing. which is that last term, which is balanced, which I really haven't defined because it honestly depends on your algorithm. Some trees, some self-balancing trees like red-black trees use variations or various different definitions to define what a balanced node is or balanced tree is. But in general, the point of a balanced tree, the effect. So let's just first talk about the effect of a tree being balanced before we can talk about the definition. The effect of a tree being balanced is that the tree's average runtime is O log n, but its worst case scenario is O of n, right? A good example of a poorly balanced tree is actually fairly straightforward to construct. We can just simply use so T, H, E, and then let's see, quick would go Q, R, S. So the quick, brown, so the quick, I forgot to do a U. So U would go here. Actually, no, but he would go here. You would go here. Apparently, I forgot how to do my ABCs, and this is not turning out as bad. But if you go across the middle row of the keyboard, that actually produces a fairly unbalanced tree. But if you keep doing this, it will get very unbalanced very quickly. Yeah. And the entire point of an unbalanced tree is, and so if a tree gets too unbalanced, everything starts to approach the O of n runtime. Even an easier example of an unbalanced tree is if I just simply do the letters A, B, C, D, E, if I just simply do them in alphabetical order. And now we've just got a linked list with extra steps, right? Okay. So the effect of a balanced tree is that we aren't talking about average anymore. We're talking about all runtimes are O log n for a balanced binary tree. That's the effect we want to have, because what we want to do with a balanced tree is that basically we have our node, okay, and then half the remaining choices are over here, and then half the remaining choices are over here, approximately a half, right? I can live with a quarter every so often because that's still cutting out a big chunk of runtime, right? But as long as we're like reducing by a significant fraction, that's going to be fine. Okay. So the way you can kind of enforce this is by giving it a proper definition. It's a recursive definition. Basically, a tree is balanced if it meets two conditions. One, left and right are the left tree and right tree are balanced, right? That's condition number one, the recursive definition. I know, it's balanced if the left and right are balanced. And two, the heights, and you can do these in either order, heights of left versus right differ, they differ by no more than one. So basically, as long as the difference in heights is less than or equal to 1, we're not too worried, right? And that will give us a balanced tree. It's a pretty straightforward definition, and it can be done recursively. That one can be done recursively. In fact, done with a recursive tract. In fact, this part demands it be done recursively. Balanced is important for trees. That's what guarantees our log n runtime. Heaps are a bit different because they just simply guarantee a log n runtime by on various operations. Let's see, what does it differ? It guarantees log n add by simply making sure that's always a complete tree. So for those of you who haven't watched the video yet, heaps are special. Heaps basically look like trees, but they perform differently. The entire point of a heap is to create something called a priority queue. The idea behind a priority queue is that queues are great, but sometimes you need to cut in line. Let's go and talk, like for instance, a hospital setting, right? If you've ever had the unfortunate circumstance where you broke a bone, right? That is what I would get classified probably as a minor or moderate injury, because as soon as you're stable, it sucks, but guess what? Your life isn't in danger. Typically, things where you are, when you hear about a news report and say somebody was severely injured, that means they're probably going to die without any. That means that their injury is such that they will die without any medical attention. Okay. The entire point of when you go into a hospital, the first thing they do is something called triage, and that's where they kind of figure out where you are in this classification of being treated. And then they will treat you when you get to you. Things like head injuries, where they don't know where they don't know how bad it is, necessarily without checking, that gets you in pretty quickly. Don't lie about your injuries, though. The doctors really hate that, and they could, they can make you wait.
Oh, they'll put you right back in the waiting room.
They'll make you wait for certain things, or if you need painkillers, suddenly that might be hard to get for a bit. On the other hand, something where it's, again, like a injury, as soon as it's been, stitched up or taken care of, right, that can wait. That's minorly injured. Okay. Again, I'm not a medical professional. I wouldn't necessarily know what classification goes into what internal code you use, but we can simply assume that, like, basically that in a hypothetical hospital, you might have a ranking of 1 to 5. And basically, we want to make sure that the people who come in with 1s are seen first in the order that they came in, so they wait for the least amount of time. Then the people who are ranked 2 get seen in order of when they came in. So basically, if you came in at 10 o'clock and then with a rank 3, and then you came in, and another person came in with 10:05, you want the person who came in at 10 with the rank 3 to be seen before the person with the injury who came in at 10:05. This is what a priority queue is. Basically, it's a system for some people to cut in line for queue. And so there's a lot of real life circumstances where we have classifications about things being important versus urgent, right? So the way that a priority queue works is that we use something called a heap. I'm going to call what's called a min. I'm going to demonstrate this by drawing something called a min heap, which is the version where we say, hey, if the number is smaller, it's more important, right? Number 1 is more important than number 100. Okay. So the way the min heap works is that you add a number to the heap, an empty heap, boom. Okay, this is now the top of the heap, the root of the heap. Add another number, and the way this works is that the number gets added to the next available slot in a, and I'll just draw like this. The number gets added to the next available slot in a complete tree. So this is currently a complete tree with 1 node. So the next available slot is this one over here. Now 1 is more important than 5, and now when we add to the bottom, what we do is we check against our parent. And we ask, am I more important than my parent? Or another way to think of this is, am I lighter than my parent? And if I'm lighter than my parent, I'll bubble to the top. Or if I'm more important than my parent, I'll swap with my parent. Okay, so 1 is more important than 5 or lighter than 5. I like using the weights sometimes because that works, and so I swap with them. Okay, next, if I do 3, that's fine. It'll stay right there. Let's go with 4. Next, 4 is lighter than 5, so it will bubble to the top and swap with 5. And then it's heavier, 4 is heavier than 1, so it's going to stay put. Okay, let's go ahead and do, I'm going to basically make this as simple as possible. We'll do a 6, a 7, and an 8. And then I'm going to go ahead and add a, come on. I'm going to go ahead and add a 0 right here. 0 is lighter than 5, so it's going to swap with 5. Okay, 0 is lighter than 5, so it's going to swap with 5. It's lighter than 4, so it's going to swap with 4. And then 0 is lighter than 1, so we'll swap with 1. This will be a question on your exam, not necessarily these numbers in these orders, but doing something like this is a 6-point question on your exam. Okay? Now, how do I resolve? So now this is adding a number to the heap. Now I ostensibly remove anywhere in the heap, but generally you're removing from the top of the heap, especially in priority queue, that's what you care about. So how does removal work? Removal works kind of in the opposite way of addition. First off, we're going to assume that we're moving the top for sake of argument, and then it works basically the same way for everything else. What we do to remove the top is, so first thing we do is remove the top, but we don't want an empty spot. We need to replace it with something. So we're going to replace it with the last item in the heap, right? Right, and heaps go, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to replace it with the last item here. And we'll just move it to the top. So now obviously this is no longer correct, but we have a way of easily solving this, which is just kind of remember that heavier lighter thing, right? 5 is heavier than its children, so I check 5 against its children. 5 is heavier than its children. I'm going to swap it with the lighter child because the lightest thing will bubble to the top. Make sense? So swap it with 5. So swap 1 and 5, and then I've got 5 is lighter than 4. Sorry, 5 is heavier than 4, but not 6. So we're just going to swap with 4. Now, all the operations in here took log of n time. Why? Because if you have n nodes, you're going to have log base 2n layers. Okay? And so an addition operation, worst case scenario, will take log n to add something, and then because that's the maximum number of swaps you'll have to make to get to the top. And then if you are removing something, it's going to also take log n for maximum swaps to sink back down. So it's a very efficient data structure in that manner. And we use it again for those for these priority heaps. Yes? Priority heaps.
Let's say 4 is a 10.
Yeah.
When it goes down a node, would it check the left one first and then the right?
When we add a node, it will. So if this was a 10 and it was sinking, we'd always swap it with the lighter child. We check both of them, right? If it's we check both of the children, and if only one child is lighter, we swap with that one, obviously. But if they're both, we have to make a decision. Now, the difference between one of the big differences between a heap is that it's pretty much always done as I would say or at least I always do it as a array-based structure as opposed to a reference-based structure. Because this is easily embeddable into an array, you just simply put it into an array like this: 1, 4, 3, 5, 6, 7, 8, where it's just simply we read across it in what's called I'm blanking on the term, but basically we're going in basically the left to right order. Okay, and then there's a formula which I go over in the videos, which basically says, given a position, I know what my children are going to be, and I know what my parent is going to be. You don't need to know that formula for the exam, but simply put, it's part of the reason why. But since it's an easy formula, just the formula takes constant time to produce, so to produce a result. So it's again just log n, and you're swapping items in an array. This tree-like structure is what we visualize it, because it's easier to look at this at the tree structure and go, aha, one's children are 4 and 3 in this structure, rather than looking at this and saying, 4's parents are 4's children are 5 and 6. The other big, so there will be 3 or 4 questions related to heaps on the exam. The first 2 you just kind of mastered already if you've been watching, which is the bubble up, bubble down kind of thing. There are such things as max heaps where the rules are reversed, but I almost always do min heaps on the exam, because if you can do a min heap, the max heap is just simply flipping the operators around. The other thing we do for that is something called Huffman encoding, which you'll need to watch the videos on, but that's how you do something called lossless compression. In the past, I've done a bit of a show of what lossless compression versus lossy compression is, but I'm going to give a few minutes rundown so that we can talk so I can go and help you. So part of what we do to, so if you've watched anybody watched the TV show Silicon Valley on HBO ever? I believe the premise, at least of the first season, was that somebody came up with a brand new spanking compression algorithm that was like better than other algorithms. And that would actually be a really awesome thing, because compression is how we make sure that things can transmit across the web without an absurd amount of data being taken. Because, well, simply put, often when we capture things with video cameras, there's a lot of information that gets captured that the human eye is not going to bother checking out, that the human eye just can't handle. For instance, if you're watching it on, if you're watching basically something that was taken that shot in 8K or 12K, if you've got a 4K TV, that's not going to do anything for you, because all those extra pixels are just extra processing for your CPU to do. So you want to compress that down to 4K. But actually, depending on how close you are to the screen, your eyes aren't really going to tell the difference between between something that's 4K or 1440p or 1080p. Just depending on how close or how far you are from the screen. The further you are away from the screen, the less fidelity you need. Okay.
For the love of God, please don't just go right up to the pixel and just straight up stare at it.
It's
I like your eyes to actually work after this.
and so there's various compression and furthermore, not necessarily. You don't necessarily need to embed every pixel like, okay, this is this pixel, this is this color, this is this color. You can be smarter about it and also say, hey, this group of pixels is this color. Long story short, we can throw out data in music and video, and it's not going to matter for a lot of circumstances. And we can make that choice as to how big the file is versus the nice fidelity of the file. In fact, if you've ever pirated a movie, you've probably done that, as opposed to like, am I going to get a higher quality shot, or am I going to get a lower quality thing? On a more benign example than piracy, if we simply let's go ahead and go to YouTube, right? If we go to YouTube, right? If we go to, let's go to, Crash Course is pretty good. And if we go to one of Crash Course's videos, Crash Course is a great channel.
This morning was a typical morning.
So if you go over here, right to the gear, you've got basically the quality, which is different levels of compression, right? And we can see that if we turn it all the way down, it's going to be a very tiny.
This morning was a typical morning for me. I woke up thinking about that dream.
But you notice that basically it's a lot harder to read details. It's a lot harder to check out things because there's only 144 horizontal lines worth of pixels that are being expanded into 1080p. They're being expanded to 1080 pixels on my screen. Whereas if I boost it all the way up, everything becomes sharper because there's a lot more pixels, a lot more, right? And simply put, that's a lossy version of compression. For video, that's okay because we can still get the general idea. However, there's various things that you need lossless compression for. Text is one of the big ones. And whenever you compress a file into a zip file or something else like that, or an executable, yeah, you don't want to throw out any of the lines of code. You probably need those. So one of the things I go over in the Heap videos, I'll end it here, is something called Huffman encoding. And that is a fairly good example of the issue of the things we need to do to handle compressing data in a lossless manner. And there will be a question on building that on the exam. Okay. And with that, I think I've eaten up enough of your time. So I'm going to go around the room now and help.